You are orbiting a star 100 light years away, and you don't even know its name. But from Earth, we can tell that something like your planet tugs on that star by less than a walking speed of 1 meter per second. From that tiny wobble across a trillion kilometers of space, we can say there is a world there. Astronomers call these worlds exoplanets, planets that orbit stars beyond our sun. We've confirmed more than 5,000 of them so far, and catalogued thousands more candidates. Some hug their stars so tightly that a year is shorter than an Earth day. Others are so puffed up and low density that they'd float in water. But here's the puzzle. We have never actually seen most of them directly. They are too small, too faint, and completely drowned in the glare of their stars. So how do we know they exist, let alone study their extreme properties in detail? The answer is beautifully indirect. We watch the stars and we look for what their planets do to them. A planet is tiny, but its gravity, its shadow, and even its atmosphere leave signatures in starlight that we can measure. Think of it as cosmic forensics. We never see the culprit, but we can reconstruct the entire crime from the clues left at the scene. The first major method is something called the radial velocity technique, often nicknamed the wobble method. Gravity is mutual. When a planet orbits a star, it's not exactly true that the planet goes around the star. Instead, both the star and the planet orbit their common center of mass, called the barycenter. For a massive star and a much smaller planet, that barycenter is usually still inside the star, but not at its exact center. So as the planet goes around, the star executes a small orbit of its own, a subtle dance. Now imagine watching the star from far away, along the same plane as the orbit. As the star moves slightly toward you, the light waves it emits are compressed, shifting very slightly toward the blue end of the spectrum. As it moves away, the waves stretch, shifting toward the red. This is the Doppler effect, the same phenomenon that makes the pitch of an ambulance siren rise as it approaches you and fall as it passes. In practice, astronomers record the star's spectrum, its detailed rainbow of colors, split into thousands of wavelengths. Embedded in that spectrum are dark absorption lines, fingerprints of specific elements like hydrogen, calcium, and iron in the star's atmosphere. When the star wobbles, those spectral lines slide back and forth in wavelength by a tiny amount. Measuring those shifts over days, months, or even years lets us reconstruct the star's motion along our line of sight, the radial velocity. The scale of these measurements is absurdly precise. For some exoplanets, the star's speed change is less than 1 meter per second. That's roughly human walking speed, measured at interstellar distances. Instruments like the HARP spectrograph in Chile and ESPRESSO on the Very Large Telescope can detect changes in wavelength of a few parts in 100 million. By fitting the measured radial velocity curve with Kepler's laws of orbital motion, astronomers can estimate the planet's orbital period, the shape of its orbit, and at least a minimum mass. But there's a catch. The radial velocity only tells us the component of motion along our line of sight. If the orbit is tilted, we see a smaller wobble than we would looking exactly edge on, so the true mass could be higher. That's why radial velocity planets are often listed with minimum mass. Still, this was enough to reveal some of the strangest early discoveries, like hot Jupiters, gas giants as massive as or more massive than Jupiter, but orbiting their stars in just a few days at distances closer than Mercury's orbit. Their huge gravitational pull produces big, easily measured stellar wobbles. The second major technique uses not motion, but shadows. It's called the transit method. If the orbit of a planet happens to be aligned so that, from our perspective, it passes directly in front of its star, then once every orbit the planet will eclipse a tiny fraction of the star's light. The star doesn't disappear, of course. It just gets a little bit dimmer. For an Earth-sized planet crossing a sun-like star, the dip in brightness is about 0.01%, 1 part in 10,000. Detecting that is like noticing if a stadium full of 10,000 lights turned off exactly 1 light bulb. From a series of these dips, astronomers can extract a surprising amount of information. The time between successive transits gives the orbital period. Using Kepler's third law, which relates orbital period to orbital distance and star mass, we can estimate how far the planet is from its star. The depth of the dip tells us the area of the planet relative to the star. Since the star's radius can often be measured independently, That ratio gives us the planet's radius in kilometers. In other words, transit data directly measure planetary size. If we combine transit data with radial velocity measurements for the same system, we get both the mass and the radius of the planet. From those, we can calculate its average density. A high density, like 8 grams per cubic centimeter, suggests an iron-rich, rocky world. A low density, like 0.3 grams per cubic centimeter, less than Saturn, suggests a gas or puffy planet with a huge hydrogen-helium envelope. This is how many of the most extreme planets in our catalogue reveal their true character, not just as dots, but as physical worlds with bulk composition. To make transit searches efficient, you want to watch tens or hundreds of thousands of stars at once, with stable, uninterrupted monitoring. That's where space telescopes change the game. The Kepler Space Telescope, launched in 2009, stared continuously at a single patch of sky in the constellations Cygnus and Lyra, tracking the brightness of about 150,000 stars every 30 minutes. No day-night cycle, no weather, no atmospheric twinkling, just ultra-precise, long-term light curves. Kepler's detectors could routinely measure brightness changes smaller than 100 parts per million. Over its primary mission, it found over 2,600 confirmed exoplanets and thousands more candidates. Among them were ultra-short-period planets that circle their stars in less than a day, tightly packed planetary systems with 6 or more worlds crammed closer than Mercury's orbit, and planets in or near the so-called habitable zone, where liquid water could exist on the surface of a rocky planet given the right atmosphere. Kepler had a bias, though. For a planet to transit from our viewpoint, its orbit has to be almost perfectly edge-on, which is a geometric coincidence. The probability of that alignment decreases as orbital distance increases. Earth's chance of transiting the Sun as seen from a random direction in space is only about 0.5%, so the vast majority of planets in the galaxy do not transit relative to us. This means Kepler was most sensitive to close-in, short-period planets with many trans.